The criticality of an instrumented function on a process plant is a measure of its importance to the continuing smooth operation of the plant. Any disturbance to a critical function will have an impact on production and may take the process into an unstable or unsafe condition or shut the plant down. Functional grouping is a determination of the instrumentation that relates to a particular control or trip function, or a group of closely interrelated and interacting control and/or trip functions. The Criticality Assessment and Functional Grouping Report for a control and safety system modification project is required to determine the criticality of instrumented process control loops and instrumented protective functions, functional grouping, relationships and interactions between loops, risks associated with loop and Fieldbus failures, and various risk mitigation methods during the modification of the plant control system. The report can then be used to determine the requirement for the detailed sequence of the cutover activities for any system which has been planned as a hot critical cutover. This document outlines the philosophy behind the development of a functional grouping and criticality grouping report, and provides generic procedures and templates which use these ratings to determine the cutover methodology. Functional grouping. The methodology adopted in this study involves the following principal steps. Functional grouping segregates the plant into various systems and subsystems. A system comprises the minimum grouping of plant control functions and associated interdependent equipment with a common purpose. In general, a functional group is a group of equipment with a common or interrelated set of control and/or trip functions. Failure of any part of the functional group will have an effect on the functional group as a whole. Within each functional group system, there may be independent functions that can be further identified as subsystems. Grouping of various subsystems shall be carried out using this functional grouping and criticality assessment philosophy, the process engineering flow schemes, PEFS, the relevant safeguarding narratives and/or control narrative documents, logic diagrams, and loop diagrams. The system or equipment items and their boundaries shall be defined and listed. For established or currently operational areas, PEFS drawings and plot plans may be used to ensure that all equipment is identified and considered. Safety instrumented system functional groups. An IPF loop consists of one or more initiators, including all components from the process connection to the IPS output card, the IPS, and one or more final elements, including all components from the output card to the actuated device. For functional grouping, we can define the group as having a common output logic function. One or more of the individual inputs may also be part of another function, in which case cutover may require temporary parallel operation of both the new and old systems. Control system functional groups. Control system functional groups normally relate to the control of a process unit, such as a vessel or reactor, where, for example, a pressure, level, temperature, and flow may be related to each other and the control of a group of valves. Functional grouping report. Based on the system, subsystem segregation, and subsequent analysis, functional grouping reports shall be prepared for the IPS and control system cutovers in 2007 and 2008. The functional grouping report format has been defined to ensure clarity and comprehensive documentation. Criticality assessment. Applicable codes and standards. D32.80.1010-Gen. Classification and implementation of instrumented protective functions. ISATR 91.002-2003. Criticality Classification Guideline for Instrumentation, AG 181 Rev 2. Fieldbus Foundation System Engineering Guidelines, HCF Lit 34. Heart Communication Foundation Field Communications Protocol Application Guide. Criticality Assessment. Applicable codes and standards, DP 32.8.10.10-Gen. Classification and implementation of instrumented protective functions, ISATR 91.22-2003. Criticality Classification Guideline for Instrumentation, AG 181 Rev 2. Fieldbus Foundation System Engineering Guidelines, HCF Lit 34 Heart Communication Foundation Field Communications Protocol Application Guide. Task. Criticality Classification General Principles. Evaluate the system and equipment item in terms of life safety, environmental hazard, plant safety, and potential production loss if the system fails. This enables those items which are non-critical, due to their insignificant failure consequences, to be objectively identified as not requiring a criticality analysis. Those systems or equipment items whose failure consequences are significant and where serious risks to health, safety, and environment, or where unacceptable economic impact will result, must be further analyzed in terms of their subsystems or components. The control system responds to input signals from the process and generates output signals to maintain operation of the process in a desired state. Conventional, not safety-certified control systems do not perform functions assessed as SIL-1 or higher. SIL-1s, SIL-2, SIL-3, instrumented protective functions. IPFs are generally ESD systems, fire and gas systems, HIP systems, or machinery, such as centrifugal compressor protection systems. Generally, an IPF is SIL rated, and the degree of criticality is related to the SIL allocated to the function concerned. Refer to IPF classification documents for specific details. Each protective function shall have an assessment of its criticality based on its SIL rating, SIL-1, SIL-2, or SIL-3. Any SIL-0 systems can be removed without impacting safety. Therefore, there should be no criticality associated with them. Note that failures of the safety system do not in themselves create a hazard, but a failure may lessen the chance of dealing with any hazard arising. Class C2, Safety Critical Control Systems. This defines control systems that have the primary function of keeping the process parameters within safe operating limits. Failure of these systems has the potential to cause a potentially hazardous situation to arise, but does not require the detection of and protection against a specific emergency condition within the control system itself. These systems may be backed up by a primary protection device, such as a pressure safety valve, or by the instrumented protective system, in which case the safety criticality requirement on the control system may be reduced. But the potential for plant depressurization or shutdown exists, with possible expensive consequences, leading to a revenue loss situation. It is a feature of safety-critical control systems that they should be robust, redundant, or fault-tolerant to avoid spurious shutdown, and as they are backed up by an IPF or primary safety device, such as a PSV, they are not necessarily designed to be fail-safe. Critical systems are required to have a very low rate of failure, probability of failure on demand. A formal procedure is proposed to identify safety-critical control systems that are not at present part of a safety-related system and to determine the necessary availability and redundancy of such critical systems. A rough definition of safety-critical is that the associated SIL is A1 or A2, as defined in Shell D.10-Gen. Classification and implementation of instrumented protective functions, and this implies a requirement for specific levels of availability and redundancy. Therefore, failure of a safety-critical control system must be mitigated by primary protection, such as a pressure safety valve, or secondary protection by a SIL-rated and third-party certified instrumented protective system, additional levels of protection. Class C1, Critical Control Systems, Non-Safety. These are instrumented control systems that have the primary function of controlling the product quality and throughput. Failure of these systems is not considered to have the potential to create a hazardous situation, but can cause plant shutdown or deterioration of product quality and subsequent loss of revenue. A criticality assessment is required to confirm that there is no potential for a hazardous event to occur as a result of a credible failure of these systems. Otherwise, the entire control system would have to be regarded as Class C2 critical. When analyzing these systems, it is necessary to consider the process dynamics and the possibility of quick recovery from the failure, either by quickly fixing the fault or taking manual control. Class 0, Non-Critical Control and Indicating Systems. These are normally control or indicating systems that give information not directly related to the control of the flow of product through the process, the failure of which or complete removal of which would have no impact on the process other than a minor inconvenience to operations or maintenance. Criticality rating procedure. Use of the procedure. A flowsheet for initial definition is useful in identifying the areas for further analysis or increased priority. Define and list all systems or main equipment items. For practical evaluation purposes, a complete system may be too large and complex for comprehensive analysis. It may, for the purposes of assessing criticality for procurement, be appropriate to consider individual main equipment items without the need for further segregation into components. The analysis of subsystem criticality can be performed using a specific methodology relevant to the stage in the asset lifecycle of the engineering activity. Quantitative risk analysis, QRA, may be used early in equipment asset life cycles to help establish criticalities. The General System Subsystem Criticality Rating Method provides a structured approach to evaluating criticality. Having defined the system to be analyzed, it is useful to include additional comments that assist in explaining its nature or function. These may contain information regarding the complexity of the process in which the system is involved, or methods by which failure in the system may be overcome. Hazard identification process documents, such as PEF-EFSAs, operating and maintenance manuals, safeguarding system logic diagrams, and existing SIL reports, shall be reviewed to identify credible events which have the potential to cause hazards. As a minimum, the review shall identify the hazards and hazardous events of the process and associated equipment. Determine the sequence of events leading up to the hazardous events. Identify the causes of each hazardous event, including fault conditions and any foreseeable misuse. Identify the consequences of each hazardous event. Determine the likelihood and hence risk associated with the hazardous events. Determine the requirement for additional risk reduction. Establish what risk reduction measures should be taken. Record the assumptions used during the analysis, including demand rates, failure rates, human intervention, and operating conditions. Consequence listing. The likelihood of a consequence for the identified hazard is listed in this section. One or more of the following classifications should be allocated to the subsystem or equipment item to indicate the nature of the failure consequences. S. Life safety. This classification applies to those subsystems or equipment whose failure will result in a direct risk to personnel. E. Environmental. This classification applies to those subsystems or equipment whose failure will result in a direct risk to the environment. P. Plant safety. This classification applies to those subsystems or equipment whose failure will result in a significant direct risk to the plant process units or structures. H. Hidden. This classification applies when failure does not result in immediate consequences, but a further failure must occur before consequences are apparent. For subsystems or equipment in this category, the consequence of further failure should be considered, and the H classification prefixed by that of the further failure, e.g. a low-level gas leak, could be classified as SH. R. Revenue. Failure of the subsystem or equipment item will have an impact on revenue or investment return. The rate at which this impact may become significant should also be considered. This should be considered where the hazard could lead to a loss of product quality or a process shutdown. N. None. Failure results in none of the consequences defined above. Risk assessment. For each critical group, the potential risks of malfunction of the instrumented system shall be assessed. Note that the risk assessment shall be carried out only for credible cases of risk during cutover activities, considering all equipment as operational, and one of the control or safeguarding systems, old or new, in fully operational condition before and after the cutover. Risk evaluation shall be carried out for the worst credible case and not the worst conceivable case. 4 major risk categories are envisaged in this project associated with the cutover tasks: task-related, caused by the activities of persons in the workplace, as listed below. Risk for the facilities during cutover due to loss of critical control. Risks associated with plant modifications, operations, maintenance as a result of cutover. Risks related to construction installation errors. The risks associated with each hazard consequence shall be tabulated. Risks associated with process dynamics and the time taken to cut over the output. Also the feasibility of manual intervention during this period. The changeover for the identified system is hot, and as all inputs are shared, the mitigated risks are required to be no risk or low risk. If, during the cutover, it is possible to take equipment out of service by putting standby equipment into service, the risks for such cases shall be considered low. Adopting risk reduction measures and precautions further mitigates such identified risks. Risk mitigation. Wherever risks need to be reduced for the safety of man equipment, mitigation methods shall be proposed. These mitigations shall either substantially reduce the risks or eliminate them. Precaution. Whenever an event can cause a hazard, and with additional precaution in the work method, this hazard can be minimized, such actions shall be identified that can substantially reduce the risk. Selection criteria for risk control countermeasures, mitigations, and precautions. When considering countermeasures against risk, the following three important selection criteria are employed. Effectiveness. Does the selected countermeasure, mitigation, or precaution adequately control risk without compromising system performance and without introducing new hazards that also have unpleasant risk? Feasibility. Can the selected countermeasure be applied on an acceptable time schedule? Cost. Can the cost of the selected countermeasure be supported as opposed to the probable cost of accepting the risk? All aspects of cost, such as initial outlay, installation, operation, and decommissioning, should be considered. Risk for the facilities during cutover. In the context of this document, published means that the existing risk mitigation procedure is documented and made known to the cutover team. Where no procedure exists, or the existing procedure is deemed not fit for purpose, a project-specific procedure shall be produced and made known to the team. Published. General power failure during, but not caused by, cutover. Check that the UPS power available during cutover is sufficient for the old system and the new system to run in parallel. Check that UPS is fully immune to main power failure. Document the UPS autonomy time and ensure it is sufficient to maintain the plant during the longest duration cutover anticipated. Check no impact is anticipated from parallel projects or maintenance activities. Document and check assumptions. General communication failure during, but not caused by cutover. Review cutover communications equipment, such as walkie-talkies, and publish communication procedures. Human error. Review cutover staff training and experience, and cutover procedure as defined in specific cutover work packs. Additional procedures as determined by permit to work procedure to be reviewed for adequacy. Unintentional operation of field equipment due to cutover. Existing PTW procedure and change control procedure shall be reviewed and commented, amended as required. Fire alarm demand during cutover. Review existing fire emergency procedures and publish relevant portions. A fire watch must be set up when there is a bypass or an override of the plant critical control or protective systems, and specific fire response on fire detection shall be included in the cutover work packs. Gas alarm demand during cutover. Review existing gas emergency, flammable and toxic procedures, and publish relevant portions in the cutover work pack. A gas watch must be set up when there is a bypass or an override of the plant critical control or protective systems. Existing control system failure during hot cutover. Review likelihood and consequences on a case-by-case basis. Risks associated with plant operation maintenance during cutover. As the plant will be in normal production during this activity, no new hazards are envisaged to arise during the cutover operation, except those that are a direct result of the system cutover. It is assumed that no new maintenance and modification activities will be performed during cutover. During hot cutover, all DCS controls, monitoring points, and alarm points are assumed to be working normally. All individual package controls are also assumed to be working normally. Various process safety devices such as PSV, PRV, NRV, rupture discs, etc., are considered to be adequate and to be set at the required design conditions. During sharing of inputs, only one input is bypassed at any given time. Similarly, during output transfer, only the selected output is transferred from the old system to the new system when the new system is fully operational. As mentioned above, existing production facilities are provided with various levels of protection. Even though, at any time, either one input or one output is bypassed during sharing transfer, Risks related to safety protection shall be taken care of by various other layers of protection, as described above, and backed by manual operator intervention. Mechanical construction activity should have been completed inside the control room and equipment rooms, and hence fire potential and related consequences should not exist. This must be confirmed. Risk analysis summary. A formal analysis of the risks related to cutover activities shall be carried out. The risks that might be encountered during cutover, commissioning of each system related to each set of inputs, outputs, nature of the hazard, and the possible consequences shall be listed in the format. This document shall also tabulate applicable mitigation methods and the precautions to be taken while working on a particular input-output.